Finally, we're going to be talking about the fundamental theorem of algebra, and we've already done a lot with it. We just have never formalized it. What the fundamental theorem of algebra says is any polynomial has as many roots as its degree. So when we had quadratics, it had 2 roots. When we had cubics, it had 3 roots. When we have quartics, it should have 4 roots, etc., etc. The other thing you need to remember is the conjugate zero theorem, that all imaginaries will come in conjugate pairs. So you can never have just one imaginary root. You must always have 2 imaginary roots in groups of 2. All right, so let's try this first polynomial. It is x squared minus 14x plus 49 equals 0. It says state the number of solutions. Well, since the degree is 2, that means there will be 2 solutions. And it says, what are they? So I'm going to solve this one by factoring. So this is x and x, minus 7, minus 7. So x equals 7 with a multiplicity of 2, or a double root. So I did get 2 roots of 7. This one I cannot factor, so I do my p over q. So the factors of 24 over the factors of 1, which will be the factors of 24. So that's plus minus 1, plus minus 24, plus minus 2, plus minus 12, plus minus 3, plus minus 8, plus minus 4, plus minus 6, all over plus minus 1. So these are my p over q's. And if we check out which ones work, we get a negative 4 works and a 3 works. So that means I must synthetic divide to find my remaining 2 because I needed 4 total roots. So I put negative 4 into 1, 3, negative 8, negative 22, negative 24. I get negative 1, negative 6. This gives me 0. So in my compressed polynomial, I'll divide my other root of 3. 1 times 3 is 3. 2 times 3 is 6. 2 times 3 is 6. So this gives me x to the 0, x to the 1, x squared. So I get x squared plus 2x plus 2 equals 0. And again, I must do the quadratic formula on that. So the opposite of 2 plus or minus the square root of 2 squared minus 4 times a times c all over 2a. That gives me negative 2 plus or minus the square root of 4 minus 8 all over 2, which is a negative 2 plus or minus the square root of a negative 4 over 2, which is a negative 2 plus or minus 2i all over 2, which is a negative 1 plus or minus I. So my other roots are negative 1 plus I and negative 1 minus I. And I have my 4 total roots. Now another root theorem we have says given any 2 roots, you have a quadratic function. And it can be written in this form: x squared minus the sum times x plus the product. That is minus the sum times x plus the product. So we can do that with any 2 roots. So let's try that on this next one. We need a 3rd degree polynomial leading coefficient of 2. So that is f of x equals 2. And then I have zeros at 1, -4, and 5. So I'm going to do a root at 1 makes a factor of x minus 1. These two, I'm going to do this sum product rule. And I always need opposite the sum. So I'm going to write opposite the sum here. So when I take a -4 plus 5, I get 1. And I'm going to want its opposite. So that would be a -1. When I do this product, I get -4 times 5, which is -20. So this gives me the square, x squared minus 1x minus 20. So now, if I multiply this out, I like to multiply it this way. I get 20. -1 times -1 is a positive 1x. -1 times x squared is a -x squared. X times -20 is -20x. X times -1x is -x squared. And x times x squared is x cubed. That gives me x cubed minus 2x squared minus 19x plus 20. Then I still have to multiply that all by 2. So I get f of x equals 2x cubed minus 4x squared minus 38x plus 40 as my polynomial in an expanded form. So expanded form means all multiplied out. Now it says write a polynomial with leading coefficient of 1. And 1 and 2 plus I are zeros. So if 1 is a 0, I know that x minus 1 is its factor. If -2 plus I is a root, according to the conjugate theorem, that -2 minus I must also be a root. So this is especially when I want to use that sum product rule. So the sum of those, -2 plus I plus a -2 minus I, gives me -4. And the product of those, -2 plus I times -2 minus I. -2 times -2 is 4. -2 times -I is positive 2I. I times -2I is -2I. And I times -I is -I squared. So this drops out. I squareds get replaced with a -1. So I have 4 minus a -1, which is 5. Again, back here, remember I need opposite the sum. So this -4 is going to turn to a positive 4. So this gives me the square x squared plus 4x plus 5. And this would be a factored form. All right. Now it says how many zeros are real and how many are imaginary. So I want the number of reals and the number of imaginaries. This is a degree of 2. It doesn't cross the x-axis at all, so there are 0 reals. So it must mean the remaining 2 must be imaginary. This is a degree of 3. I see here I have a root at 3, but it is a triple root, so they are 3 reals and no imaginaries. This is a degree of 5. Right here, I have a root at 1, but it's a triple root, so that's 3 reals. And I have a double root here at 3, so that's 2 more, so that's 5 reals. So none are imaginary. And then this one, I have 1 real root. So since it's a degree of 3, the remaining 2 must be imaginary. Notice my imaginaries always come in pairs. Here I have 1 real, and then here I have a double root, so that's a total of 3 real. So the other 2 must be imaginary. Right? Last question. This is a 4th degree. How many are real? How many are imaginary? I see 1, 2, 3, 4 reals. So that means none are imaginary.